Hi, welcome to the second lesson on the topic of magnetism and the motor effect. This lesson is about current carrying wires and the magnetic field they create. Here we have a current carrying wire passing through a clear sheet. Now this wire, when carrying current, actually forms a magnetic field. We can use iron filings, as we can see here, to identify and visualize this magnetic field and the magnetic field lines. Slowly, if we tap this sheet, the magnetic field lines will begin to show, as you can see here, right around the wire. Once it's shaken a bit, the filings fall into place along the magnetic field lines, just like this. Let's take a closer look at what this means. So as we saw in the video, we can see that a magnetic field circles a current carrying wire. However, the magnetic field lines are in a very specific direction, and this simply depends on the direction of current flow. We can identify the direction of the magnetic field using what's called the right-hand thumb rule. Let's take a look at this diagram. Here we have a current carrying wire. And if we use the right-hand thumb rule that we can see on the right-hand side, we can see that the direction of the magnetic field lines are the same as the person's fingers. This is a very simple rule and very simple way of identifying the direction of a magnetic field. We can see that the thumb points in the direction of current flow, and the magnetic field lines follow the direction of a person's fingers. Hopefully you've got that. If you haven't, go back and watch that bit again. Now, what do you think will happen if we change the direction of current flow? What will happen to the magnetic field lines? Pause the video and think. It's very simple. If the direction of current flow is reversed, so will the magnetic field lines. You can try this by putting your hand to the screen and turning it upside down. Now your thumb should be pointing downwards, and your fingers will show that the magnetic field lines are in the opposite direction. So reversing the direction of the current reverses the direction of the magnetic field lines. Let's try a quick question. Here we have scenario A and scenario B. In both scenarios, we have a point X and a point Y. At which points, X or Y, will the magnetic field be greatest? Pause the video and have a go. So, just like we saw in the last lesson, the magnetic field will be far stronger at X because it's closer to the source. In this case, it's the current carrying wire. In the last lesson, it was a bar magnet. In scenario B, the only difference is this wire carries 5 amps of current and this wire carries 9 amps. And the greater the current, the greater the strength of the magnetic field. So Y will be stronger here. We can therefore deduce that increasing current increases the magnetic field strength, and decreasing the distance from the wire increases the magnetic field strength, just like we saw in the last question. Now let's move on to a very common application of this. This is a solenoid. It's a coil of wire that can have current flowing through it. Now this is just like another wire, but because it's coiled, the rules are slightly different. And for our exams, we need to be able to draw the magnetic field around it and identify the north and south pole. In order to do so, we need to know the direction of current flow. As we can see here, the iron filings, similar to the ones we saw in the video, have lined up along the direction of the magnetic field lines. So we can see the magnetic field lines are passing through the solenoid like this. This is very similar to the structure of a bar magnet. Now, to identify the direction of the magnetic field and identify the north pole and south pole, we need to use our right hand again. But in this case, it's going to be slightly different. First, we need to identify the direction of current flow. So in this case, current flow would be in on the left-hand side and out on the right-hand side. And using what's called the right-hand grip rule, we can identify the north and south poles. Let's take a look. This is how the right-hand grip rule works. We have currents flowing in from this side, around this wire here, therefore we can see that current is flowing in this direction. We can see that our fingers in this diagram follow the direction of the current flow around the solenoid, around the coil. And in this case, our thumb represents the direction of the north pole. This is known as the right-hand grip rule. Now, in these two diagrams, which side is the north pole? Pause the video and have a go. So, if you put your hand to the screen near the first one, we can see that if our fingers follow the direction of current flow, the north pole will be on this side, and the south pole will therefore be on this side. Now, as we know, magnetic field lines go out at the north pole and in at the south pole. So our magnetic field lines will look like this, just like the bar magnets from the last lesson. What about the one on the right-hand side? Make sure you've had a go before listening to the next part. Now in this case, it's the opposite. The north pole is on this side and the south pole is on the other side. And if we were to use the right-hand grip rule, our palm, the palm of our hands, would be facing us and our thumb on our right hand would be pointing to the right. And as we can see, the magnetic field lines would flow like so. That's it for this video. I hope you found it useful. If you have any questions, please do ask.